Hello everyone, welcome to the notes for 2-9. This is our third lesson on area under a curve. To start out, it states, write the following in sigma notation. We have 1 plus 1.5 plus 2 plus 2.5. Well, it looks like we're adding that same amount each time, right? We're adding 0.5 each time, so we can think of this as like an arithmetic sequence or arithmetic series. And therefore, if we want to do it in sigma notation, right, we could call this our 0th term, first term, second term, third term. So we'll say as the series starts with our 0th term and goes all the way to the third term of our function rule, or our argument would be our 0th term plus 0.5x number of times. You could write 0.5x plus 1 as well. That would also be correct. The second one, notice we kind of shift over to 1.5, 2, 2.5, then 3. So what was above was the first term, right? That was the second term, was the third term. So we could even treat this as this being the first term, second term, third term. This would be like the fourth term. When we do that, that prevents us from having to change our function. We know that this function rule, I need to put parentheses around that, would still work with this one because it's the same set of numbers, right? But now instead of starting with our 0th term, we're starting with the first term. So we'll say from the first term to the fourth term. And typically that's kind of like the difference between our left endpoint rectangles and right endpoint rectangles, right? If you're starting with the number that's all the way on the left, or if you're starting, like we know that the one over here would be 1, right? If this was x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, okay, notice when we have like something that's on the right endpoints, we'd start with 1 and go to 4, versus this one, right, we maybe didn't make it all the way to 3 because we had our 4 already. This was that x sub 0, x sub 1, x sub 2, x sub 3. So we would go right there. And that's what we're going to talk about a little bit more in depth today. So this last one at the bottom, can you just do that one real quick? We have 2 plus 5 plus 8 plus 11 plus 14 plus 17. Well, there's sigma, right? For our 0th term is here. That makes 1, 2, 3, 4, 5 terms away. So you're going to say x is equal to 0. We're going to the 5th term of our 0th term is 2 plus 3 times x, because that's our common difference. When we use left and right endpoint rectangles to estimate area under a curve, we are really setting up a series for which we can use sigma notation. This is like the last problem we did in the notes yesterday. So if you didn't watch that part, you could always go back and watch it if you need to. If we go back to our second slide from the previous lesson, our expanded sum was 0.5 times 1 squared plus 0.5 times 1.5 squared, all the way across till we get to the 2.5. They ask, how would this look in sigma notation? Well, notice the things that are similar in all of them, right? We have 0.5, we have the square on every single one of them. So this part is going to fall in our argument. The part that's changing is like our input value here. If I want to write this in sigma notation, I'm going to draw out my sigma. And if we just think about that sequence going 1, 1.5, 2, 2.5, you could treat this like it's the 0th term, the first term, the second term, the third term. Okay, so we'll say we're going from our 0th term to our third term of the argument defined by 0.5 times something squared. And now all we need to do is come up with a rule, right, a function rule that goes in here that fits that arithmetic sequence. So we could say our 0th term, which was this one, right, 1, and we're adding a half each time, so plus 0.5x. And that's going to help us to cut down on the amount of work that we have to do to find the sum. That is our sigma notation. If we go back to our third slide from the previous lesson, our expanded sum was 0.5 times 1.5 squared, and then all the way up to 3. So how can we change the summation we just wrote to represent this sum instead? So here's the difference, right? In the previous one, we had 0.5 times 1 to the second power, right? And we found the sum from here to there. This one is asking us to take it a little bit further. We're going from here to the end. It's the same pattern that's happening amongst these terms. So as I take it here and I write out my sigma notation, if that's the same pattern that we had before, I'm going to write 0.5 times something squared. Well, that something we said before was 1 plus 0.5x. But now, if this was our 0th term, this was our first, second, third, fourth terms. For our green one, we're starting with this first term. So we're going to say let x equal 1, and we're going to the fourth term instead. And that's how we would represent that green series that's up here. Okay, so we use that same function rule, we just changed these values because they matched up. I'm not sure what this whole number 1 on worksheet 10 was. I think I forgot to take that out, so I don't believe we have a worksheet 10, so just ignore that part, please. The estimated area, we had 1/2 times 2 to the negative first, and this was that last problem from yesterday, plus 1/2 times 2 to the negative 1/2, and all the way across till we get to the 1.5. We did write this out yesterday. Don't look back at your notes. See if you can do it from memory right now. So we've got sigma. Right, remember, this is the part that has the actual sequence in it. So that's the part that we're going to write out like a function rule for. Everything else will still be in there. We've got 1/2 times 2, and I'm going to put my exponent on the outside. It doesn't really matter which way you do it. Okay, so we said that this was like our 0th term, so we'll say x is equal to 0. 0th term, first, second, third, fourth, fifth. So we're going to the 5th term of our 0th term plus 1.5 or 0.5 times x. I think we wrote it as 0.5 yesterday. And that is going to be the way we would write that in sigma notation, which takes way less time to type into a calculator and find the sum versus typing in that entire expression above. The last slide in these notes says the area under the curve y equals the square root of x on the interval from 2 to 14 is to be approximated using 4 left endpoint rectangles. Write the summation notation that will represent this area. All right, so the key information, we've got this function, y is equal to the square root of x. We've got our interval from 2 to 14 using 4 left endpoint rectangles. So the first information I want to find real quick is my delta x. I'm going to do 14 minus 2 over 4, which is going to give us 3. And if we think about, if we were going to take this and graph all of this, I'm not going to do a full graph, but I'm just going to give you a visual so that you can follow along. Right? We know that our x sub 0 would have been 2, and we would have added 3 to that to get 5. That would be x sub 1. We would have added 3 to that to get 8. That's our x sub 2. We've got 11, which is our x sub 3. And then we've got 14, which is our x sub 4. And each of those would have been the base for one of our rectangles. right? We have a rectangle here and here, and then a rectangle here and there. So our base for each of our rectangles would have been 3. And then we would have to have figured out what the height was going to be for each of them. And remember, if it's a left endpoint, that means we would have started on this side. So this first rectangle, actually, let me just kind of sketch in the rectangle. I don't know what the heights are. I'm just drawing in some random rectangles there. But remember, our left side, right? So we'd be starting with 2, and then we would have one using our x sub 1, which is 5, our x sub 2, which is 8, and then our x sub 3, which is 11. These are for left endpoint rectangles. In order to find the area under this curve in summation notation, right? So let's first of all, let's put our sigma in. We know that we would be using from our 0th term all the way to our 3rd term. We can go ahead and put that on there. X is equal to 0 all the way to 3. And then if we were trying to figure out what the argument is going to be, remember each of these rectangles has a base of 3. So we're going to be doing 3 times the height, right? This is like base times height. Well, our heights, right, are going to come from this expression. It's like we'd be doing like the square root of 2. And then we'd be doing the square root of 5. We'd be doing the square root of 8 and the square root of 11. So we're going to be taking the square root of all those different values. Okay, so we need to have a rule that gets us these values. And since we're just adding 3 each time, this is just like an arithmetic sequence. Just think about those values, 2, 5, 8, 11. So we would say here that would be like saying f of x is going to equal, our 0th term is 2, plus, we're adding 3 each time. That's like our slope or our common difference, plus 3 times x. Okay? And that is what we are going to have inside of our square root. We'll say 2 plus 3x. Right, you don't need that base and height underneath there. That's just so you can see that. That would give us the area under the curve for this. So that's just the summation that will represent it. Now it asks us to make one small change so that the summation represents the estimate using right endpoint rectangles. So let's think about it. Okay, so if we want to have this for right endpoint rectangles, okay, we still want to just keep that same expression. We're still using the same values here. But now, right, we're not going to be using the left endpoint. Our first rectangle is going to be used here with 5. Our second rectangle is going to be used with the 8. Our third rectangle is going to be used with the 11. And our fourth rectangle is going to be used with the 14. So now we're going to be going from x sub 1 to x sub 4 using that same function rule. So we'll say x is equal to 1 on the bottom, and then we're going to put 4 on the top. That's the easiest way for us to change it so that we will end up getting a correct value using the right endpoint rectangles instead of the left. So just to summarize, for left endpoint rectangles, they're always going to start with x equals 0. For right endpoint rectangles, they're always going to start with x equals 1. Hopefully that makes sense, but that's really important. That's one of the most important parts. So left always start with 0, right always start with 1. If you have questions about this, reach out to me. We'll help you out and get you all squared away. All right, thanks for watching.